Look up at the night sky. What do you see? Stars, planets, maybe a distant galaxy if you're lucky. But here's the astonishing truth. Everything we can observe, everything we've ever discovered with our most powerful telescopes, makes up less than 5% of the universe. The rest, an invisible, enigmatic realm of dark matter and dark energy, two of the greatest mysteries in modern science. These hidden forces don't just exist at the edges of our understanding. They dominate the cosmos, shaping galaxies, accelerating the expansion of the universe, and defying the very laws of physics as we know them. Yet, despite decades of research, we've barely scratched the surface of what they truly are. Imagine a puzzle where 95% of the pieces are missing. That's the challenge scientists face when trying to unravel the secrets of dark matter and dark energy. Dark matter acts like an invisible scaffold, holding galaxies together with its gravitational pull, while dark energy pushes the universe apart at an ever-increasing rate. They're opposites in their effects, yet both remain utterly mysterious. We can't see them, we can't touch them, and yet their influence is everywhere. What if I told you that right now, as you watch this, streams of dark matter are passing through your body without you even noticing? It's a haunting reminder of how much we still don't understand about the fabric of reality itself. This journey isn't just about scientific curiosity, it's about rewriting the story of our universe. Over the next 30 mysteries, we'll dive into the most mind-bending questions that keep cosmologists awake at night. Could dark matter be made of undiscovered particles? Is dark energy a property of space itself, or something even stranger? From ghostly signals in deep space to the eerie voids where galaxies refuse to form, each mystery peels back another layer of this cosmic enigma. So if you've ever wondered what lies beyond the limits of our knowledge, buckle up. We're about to venture into the unknown, where the answers might just change everything we thought we knew. In the 1970s, astronomer Vera Rubin made a discovery that would shake the foundations of modern physics. While studying the Andromeda galaxy, she noticed something strange. Outer stars were orbiting just as fast as those near the center. According to Newton's laws, these distant stars should have been moving slower, like planets farther from the sun, but they weren't. The galaxy's rotation curve was flat, defying every prediction. The only explanation, an enormous amount of invisible mass must be holding everything together far beyond what telescopes could see. This was the first undeniable evidence of dark matter. Think of it like a merry-go-round. If all the weight sat at the center, the outer edges would barely move. But imagine invisible hands pushing outward, adding unseen mass suddenly. The whole platform spins uniformly. That's exactly what's happening in galaxies. Visible stars and gas clouds are just the tip of the cosmic iceberg, floating atop a vast sea of something we can't detect. Later studies of other galaxies confirmed Rubin's findings. No matter where astronomers looked, they found the same discrepancy. Galaxies behave as if they contain 5 to 10 times more mass than what's visible. This missing mass problem isn't just about one galaxy, it's a universal flaw in our understanding of gravity and matter. Even Einstein's theory of general relativity, which perfectly predicts the bending of light around massive objects, falls short without dark matter's hidden influence. Some scientists propose tweaking gravity itself, suggesting our laws might be incomplete. But alternative theories struggle to explain all the evidence, from the way galaxy clusters collide to the intricate patterns in the cosmic microwave background. Dark matter remains the most elegant solution, even if we still don't know what it's made of. The implications are staggering. If dark matter outweighs ordinary matter by such a huge margin, everything we see, every star, planet, and living thing, is just a ripple on the surface of a much darker, stranger cosmos. And Rubin's discovery was just the beginning. Her work forced us to confront an uncomfortable truth. The universe isn't just expanding, it's built on shadows. One of the most awe-inspiring snapshots in modern astronomy isn't a glittering nebula or a swirling galaxy. It's the aftermath of a cosmic car crash. The Bullet Cluster, two galaxy clusters colliding at millions of miles per hour, gave us something extraordinary, a visible map of dark matter's ghostly presence. When scientists first studied this violent encounter, they expected the mass of the clusters determined by gravitational lensing, where the cluster's gravity bends light from objects behind them, to align with the glowing clouds of hot gas visible in X-rays. But the universe had a surprise in store. Here's what happened. As the clusters slammed together, their stars passed right through each other like ghosts barely interacting. The hot gas clouds, however, collided and stalled in the middle like two jets of water hitting head-on. But when astronomers measured the gravitational lensing effect, they found most of the mass wasn't where the gas was. Instead, it had sailed ahead on either side, perfectly matching the locations of the stars. This meant something invisible, something that didn't collide or slow down, was carrying the bulk of the cluster's weight. Dark matter had literally been caught separating from ordinary matter. The Bullet Cluster became a smoking gun because it ruled out alternative explanations. If the missing mass were just hidden ordinary matter, it would have behaved like the gas piling up in the center. If Einstein's gravity laws were wrong, the lensing pattern wouldn't have matched the star's position so precisely. But the evidence was undeniable. Dark matter doesn't interact with light or other matter except through gravity, letting it breeze through the collision untouched. It's as if two crowds of people ran into each other, but only their shadows kept moving forward while their bodies got stuck. This discovery reshaped cosmology. For the first time, we weren't just inferring dark matter's existence from galaxy rotations, we were seeing its gravitational fingerprint directly. Subsequent studies of other colliding clusters, like MAX J0025, showed the same eerie separation. Each collision acts like a natural laboratory, revealing dark matter's stubborn independence from everything we can see. Yet for all these breakthroughs, the Bullet Cluster deepened the mystery in another way. It proved dark matter isn't just a placeholder in our equations. It's real, it's out there, and it's playing by rules we're still struggling to decode. If there's one thing cosmologists love, it's a tidy model, a framework that explains the universe's behavior with elegant precision. For decades, the lambda-cold dark matter model, or lambda CDM, has been that golden standard. It paints dark matter as slow-moving, invisible particles that clump together under gravity, forming vast halos around galaxies. These halos act like cosmic glue, holding galaxies together and shaping the large-scale structure of the universe. But recently, something unsettling has emerged. The real universe isn't playing by lambda CDM's rules. Take dwarf galaxies, for instance. These tiny, faint galaxies orbiting larger ones like the Milky Way should be dominated by dark matter according to the model. But some, like NGC 1052DF2, defy expectations entirely. Observations show it contains almost no dark matter, a cosmic ghost town where there should be an invisible anchor. On the flip side, galaxies like Dragonfly 44 are nearly 99% dark matter, a bizarre mismatch with the surrounding cosmos. It's as if the universe handed out dark matter like a capricious chef. Some galaxies get a heaping portion while others are left with crumbs. The contradictions don't stop there. Lambda CDM predicts that dark matter halos should be dense at the center and fuzzy at the edges, creating a specific gravitational profile. Yet when astronomers study the motions of stars within galaxies, many halos appear more evenly distributed, a core vs. cusp debate that's been raging for years. Even stranger, some ultra-diffuse galaxies with stars spread astonishingly thin somehow still have the gravitational grip of a much heavier object. So what's going on? Some theorists suggest dark matter might be more complex than we thought, perhaps interacting with itself through unknown forces or even decaying over time. Others wonder if our understanding of gravity needs a radical overhaul. Then there's the tantalizing possibility that dark matter isn't one thing but many, a mix of particles with different properties, like a cosmic buffet of invisible ingredients. Every anomaly chips away at the clean simplicity of lambda CDM, forcing scientists to ask uncomfortable questions. Are we missing a fundamental piece of the puzzle, or is the model itself fundamentally flawed? The diversity problem isn't just a technical hiccup, it's a crisis of cosmic proportions, revealing how much we still don't understand about the dark scaffolding of the universe. And until we solve it, the true nature of reality remains hidden in the shadows. Deep beneath the Earth's surface, in abandoned mines and mountain tunnels, scientists have built some of the most sensitive detectors ever conceived, not to find gold or rare minerals, but to catch the faintest whisper of a particle that might not even exist. For decades, these underground labs have hunted for WIMP, or weakly interacting massive particles, the leading theoretical candidates for dark matter. The premise was simple: if dark matter permeates the galaxy, countless WIMP should be streaming through Earth every second. Occasionally, one might bump into an atomic nucleus in a detector, producing a minuscule flash of light or a tiny burst of heat. But after years of searching, the results have been eerily silent, and the mystery has only deepened. Take the Dama/Libra experiment, buried under Italy's Gran Sasso mountain. Since the late 1990s, its detectors have recorded an annual signal that fluctuates with the seasons, exactly what you'd expect if Earth were moving through a wind of dark matter particles as it orbits the Sun. But here's the catch: no other experiment has ever replicated this signal. Critics argue it could be noise from cosmic rays, temperature shifts, or even subtle changes in the detector itself. Meanwhile, ultra-sensitive projects like EluX in South Dakota and Xeno-NNT in Italy, which use liquid xenon to amplify potential dark matter collisions, have found nothing at all. Their detectors are so precise they could spot a single grain of sand dropped from space, yet WIMP remains stubbornly invisible. The implications are profound. If WIMP are real, they should have shown up by now. Their absence forces physicists to confront uncomfortable possibilities. Maybe dark matter isn't made of WIMP at all. Maybe it's something even stranger: axions, sterile neutrinos, or primordial black holes formed in the early universe. Or perhaps dark matter interacts with ordinary matter in ways we haven't even imagined, slipping through our detectors like ghosts through walls. This isn't just a technical setback, it's a crisis for particle physics. The WIMP hypothesis was elegant, tying dark matter to supersymmetry, a theory that could have unified all the fundamental forces of nature. But with every null result, confidence in that vision wavers. Some researchers are pivoting to alternative detectors, like quantum crystals that vibrate at ultra-low temperatures, or even repurposing GPS satellites to hunt for dark matter's subtle tug on atomic clocks. Others are re-examining the data, asking if we've missed something fundamental. The silence underground speaks volumes. It tells us the universe is far stranger than we thought, and the answers we seek might lie beyond the limits of our current tools. Until then, the detectors keep running, listening for a signal from the dark. While WIMP have dominated the dark matter conversation for decades, there's another contender lurking in the shadows, one so tiny it could rewrite the rules of particle physics. Meet the axion, a hypothetical particle so lightweight it makes an electron look like a boulder. Born from an attempt to solve one of quantum mechanics' most perplexing puzzles, the strong CP problem, axions have quietly emerged as a leading alternative to WIMP. Here's the twist: if they exist, they'd not only explain dark matter, but also fix a glaring inconsistency in our understanding of the fundamental forces that hold atoms together. The strong CP problem is a head-scratcher. In the subatomic world, the strong nuclear force which binds quarks inside protons and neutrons should, in theory, violate something called charge parity symmetry. This violation would leave traces like electric dipole moments in neutrons, but experiments show none. It's as if a destructive force keeps cancelling itself out perfectly, and no one knows why. In 1977, physicists Roberto Pexi and Helen Quinn proposed a solution, a new symmetry that, when broken, would generate an ultralight particle to restore balance. That particle, the axion, what makes axions so compelling is their dual role. Not only could they smooth over quantum mechanics' rough edges, but their sheer abundance could account for dark matter's gravitational grip. Picture this: axions would be billions of times lighter than electrons, but the early universe might have produced them in such staggering numbers that their collective mass outweighs all visible matter. Unlike WIMP, which rarely interact with anything, axions could behave more like waves, oscillating at specific frequencies as they permeate space, a cosmic hum waiting to be heard. Detecting them, though, requires a paradigm shift. While WIMP hunters rely on massive underground detectors, axion searches look more like radio astronomy. Experiments like a DMX, the Axion Dark Matter E experiment, use powerful magnetic fields and ultra-sensitive microwave cavities to tune in to axions' predicted frequencies. The idea is simple: if axions exist, they should convert into faint microwave photons in the presence of a strong magnetic field. It's like turning an invisible particle into a whisper of radio static if you can amplify it enough to hear. The challenge: axions could be anywhere on a vast frequency spectrum, and their signal would be drowned out by noise. A DMX's team compares it to searching for a single radio station in a blizzard of static, not knowing which dial it's on. Recent upgrades, though, have brought unprecedented sensitivity, scanning millionths of an electron volt at a time. Meanwhile, other projects like Haystack and Organ are exploring different frequency ranges, casting a wider net. The stakes couldn't be higher. If axions are real, they'd solve two of physics' greatest riddles at once. But if they're not, the hunt for dark matter's identity takes another sharp turn into the unknown. Either way, the axion enigma reminds us that the universe's secrets often hide in the smallest, quietest corners, waiting for the right experiment to shine a light. Supercomputer simulations are supposed to be our cosmic crystal balls, powerful enough to predict how galaxies form and evolve over billions of years. But there's a glaring mismatch between what these virtual universes show and what we actually see in the night sky. The problem has a name: the too big to fail problem, and it's throwing dark matter theory into chaos. Here's the puzzle. When scientists simulate the birth and growth of galaxies using the lambda-CDM model, they expect to find massive dark matter halos around every sizable galaxy, dense, heavy structures that should act like gravitational anchors. But when astronomers look at real dwarf galaxies orbiting the Milky Way and Andromeda, many of these halos are suspiciously missing. It's as if the universe forgot to build the foundations for skyscrapers, leaving only flimsy structures behind. The halos in the simulations are simply too big to fail. They should be brimming with stars, yet we find ghostly galaxies with almost nothing to show for them. One of the most baffling examples lies right in our cosmic backyard. Take the dwarf galaxies Segway 1 and Draco. According to simulations, their dark matter halos should be so massive they'd inevitably pull in enough gas and dust to form vibrant stellar nurseries. Instead, they're dim, star-starved husks. Even stranger, some ultra-faint dwarfs like Triangulum 2 have so few stars that their dark matter halos must be far less concentrated than lambda-CDM predicts. It's like opening a treasure chest and finding it almost empty. Nature isn't following the script. So where's the disconnect? Some theorists argue that supernovae, the violent deaths of massive stars, could have blown away gas in these small galaxies, preventing stars from forming. Others suggest cosmic tides, the gravitational tug of war between galaxies, might have stripped away their dark matter over time. But these explanations feel like patches on a deeper wound. If tidal forces were the answer, why do some dwarfs keep their halos while others lose them? And why don't simulations account for this randomness? Then there's the radical possibility. Dark matter isn't as cold or sluggish as we thought. The lambda CDM model assumes dark matter particles move slowly, clumping easily into dense halos. But if they're warmer, zipping around at higher speeds, they might resist piling up so tightly, leading to lighter, more spread-out halos. This warm dark matter idea has its own hurdles, though. Too much warmth and galaxies wouldn't form at all in the early universe. It's a delicate balancing act with no clear winner yet. The too big to fail problem isn't just a technical hiccup. It's a rift between theory and observation, forcing us to question whether we've misunderstood dark matter's nature, overlooked hidden cosmic forces, or even misread the rules of gravity itself. Every dwarf galaxy that defies the simulations is a crack in the foundation of modern cosmology, and a clue that the dark universe might be far more dynamic and more mysterious than we ever imagined. The Milky Way should be drowning in dwarf galaxies. According to the most sophisticated simulations, hundreds, if not thousands, of these tiny cosmic companions ought to orbit our galaxy, each held in place by its own halo of dark matter. Yet when astronomers peer into the night sky, they find barely a few dozen. This glaring mismatch between prediction and reality is known as the missing satellites problem, and it's one of the most persistent headaches in modern cosmology. So where did all those dwarf galaxies go? One possibility is brutally simple. They never formed in the first place. Dark matter's gravitational pull is what allows gas and dust to clump together, igniting stars and building galaxies. But if dark matter particles are too light or too fast-moving, what scientists call warm dark matter, they might not clump densely enough at small scales to birth tiny galaxies. Imagine trying to build sandcastles with grains that refuse to stick together. The result, a universe where dwarf galaxies are rarer than they should be, leaving vast stretches of dark matter halos empty and dark. But there's another twist. Maybe the satellites aren't missing, just hiding. Dwarf galaxies are notoriously faint, often containing fewer stars than some globular clusters. If they're also spread thin, like cosmic cobwebs, they could easily vanish into the background glare of the Milky Way. Recent surveys like the Dark Energy Camera's Local Volume Exploration Delve have uncovered a handful of ultra-faint dwarfs previously lost in the noise, suggesting we're only just beginning to map this hidden population. Some theorists even speculate that the darkest, most star-starved dwarfs could be almost entirely made of dark matter, invisible except for their gravitational tug. Then there's the violence of cosmic history to consider. The early universe was a battlefield, and small galaxies were often casualties. As the Milky Way grew, its gravity could have ripped apart countless dwarfs, scattering their stars into faint streams like the ghostly remains of Gaia Enceladus, a dwarf galaxy our Milky Way cannibalized billions of years ago. Others might have been stripped of their gas by intergalactic winds, leaving them too dim to spot. The mystery deepens when we compare our galaxy to its neighbors. Andromeda, for instance, hosts far more visible dwarfs than the Milky Way. Is this a quirk of our local cosmic environment, or a clue that dark matter behaves differently from place to place? The answer could reshape our understanding of how galaxies evolve, and whether the universe's dark scaffolding is more complex than we ever imagined. For now, the missing satellites problem remains a gaping hole in our cosmic map. Every undiscovered dwarf could hold secrets about dark matter's true nature, or reveal pockets of the universe where the rules bend in unexpected ways. Until we find them, we're left with a haunting question. Is the Milky Way an outlier, or are we simply missing the bigger picture? For most of cosmology's history, dark matter has been treated as the ultimate loner, a ghostly substance that barely notices itself or anything else. The standard model assumes dark matter particles drift through space without colliding, interacting only through gravity's faint tug. But what if that's wrong? A daring idea is gaining traction. Dark matter might not just clump in halos, it might interact with itself like invisible billiard balls bouncing off one another in the cosmic void. This theory, called self-interacting dark matter or SIDM, could explain some of the universe's weirdest anomalies. Take El Gordo, a pair of galaxy clusters smashing together 7 billion light-years away. When astronomers mapped its mass using gravitational lensing, they found dark matter lagging behind the visible galaxies, almost as if it had been slowed down by friction. In a collisionless universe, this shouldn't happen. Dark matter should zip right through, just like it did in the Bullet cluster, but El Gordo's dark matter seemed to drag, hinting at unseen forces at play. Think of it like two crowds merging. If people pass through each other without touching, they'll keep moving at the same speed, but if they bump shoulders, they'll slow down. That's the essence of SIDM. Dark matter might have its own hidden interactions, creating a subtle cosmic traffic jam. Other clusters, like Abell 521, show similar quirks with dark matter offsets that defy collisionless models. The implications ripple far beyond galaxy clusters. If dark matter interacts with itself, it could solve the diversity problem plaguing dwarf galaxies. Some halos might be puffier because self-interactions spread out their mass, like stirring a cup of coffee to diffuse the cream. This could explain why some galaxies, like those in the Too Big to Fail mystery, have unexpectedly wispy dark matter profiles. Even the Milky Way's missing satellites might fit the puzzle. Self-interactions could prevent dark matter from clumping densely enough to form as many small galaxies as simulations predict. Not everyone's convinced, though. Critics argue these observations might stem from ordinary physics, like turbulent gas dynamics or measurement errors. And if dark matter does interact, how does it scatter like particles in a particle accelerator, or exchange some exotic dark force carrier? Experiments are already adapting. Underground detectors built to catch WIMP are now searching for these fainter, more complex signals. Meanwhile, astronomers are scouring more cluster collisions for telltale delays in dark matter's movement. The beauty of SIDM is its audacity. It challenges the assumption that dark matter must be simple and aloof, opening the door to a richer, messier cosmos, one where the invisible majority plays by rules we're only beginning to glimpse. Whether it's right or wrong, it reminds us that the universe's greatest mysteries often hide in the subtle details, waiting for us to look closer. What if the key to unlocking dark matter's secrets isn't a particle at all, but a cosmic relic from the universe's violent birth? Enter primordial black holes, a radical twist on the dark matter enigma. These aren't the black holes formed by collapsing stars. They're hypothesized to have spawned in the seething chaos of the Big Bang itself, when dense patches of the infant universe collapsed under their own gravity. Ranging in size from a speck of dust to a massive star, they'd be invisible, ubiquitous, and if they exist in vast enough numbers, could account for every ounce of dark matter's gravitational grip. The idea isn't new. In the 1970s, Stephen Hawking and others toyed with the notion, but it fell out of favor as particle-based theories like WIMP took over. Then, in 2016, the LIGO Observatory dropped a bombshell, the first detection of gravitational waves from colliding black holes. The twist: these black holes were heavier than expected, between 20 and 50 solar masses, and their origins were unclear. Could some of them be primordial, leftovers from the universe's first moments? Suddenly, the hypothesis roared back to life. But here's the catch. If primordial black holes make up dark matter, they'd need to be incredibly common, yet somehow avoid disrupting the cosmos as we know it. Take microlensing surveys, which scan for the telltale flickers of light caused by invisible objects bending starlight. While they've spotted a few potential candidates, the numbers don't add up to account for all dark matter. Then there's the cosmic microwave background, the afterglow of the Big Bang. Primordial black holes would have injected energy into the early universe, leaving scars on this ancient light. The fact we don't see those scars suggests they can't be the dominant form of dark matter, though a smaller population might still lurk unseen. The debate gets even murkier when you consider black hole mergers. LIGO discoveries revealed pairs of black holes spiraling into each other, but how did they get so close in the first place? If dark matter were mostly primordial black holes, they'd need to cluster densely enough to pair up, yet simulations show this would also rip apart dwarf galaxies, something we don't observe. Some researchers propose a middle ground. Maybe primordial black holes make up just a fraction of dark matter, with the rest being something else entirely. Others suggest they could be hiding in the voids between galaxies, where their influence would be harder to detect. The beauty of this idea lies in its audacity. It forces us to rethink not just dark matter, but the universe's very origins. If even a handful of primordial black holes exist, they'd be time capsules from the Big Bang, carrying clues about conditions we can only theorize. And while the evidence remains inconclusive, the mere possibility keeps the door open, a reminder that the darkest corners of the cosmos might hold surprises we've yet to imagine. Picture Earth's history as a clock, with each tick marking a cataclysm: asteroid strikes, volcanic eruptions, and mass extinctions that reshaped life itself. Now imagine an unseen hand nudging the clock's gears from the shadows. That's the provocative idea behind the dark disk hypothesis, a hidden layer of dark matter, not just scattered throughout the Milky Way, but concentrated in a dense disk aligned with our galaxy's spiral arms. If real, this dark disk could be flinging comets toward Earth at regular intervals, like a cosmic pendulum swinging through time, leaving scars on our planet's fossil record. The theory hinges on gravity's subtle choreography. Most models assume dark matter forms a spherical halo around galaxies, but some physicists argue a fraction could have pooled into a flattened disk, much like ordinary matter did when the Milky Way spun into shape. This disk wouldn't just sit quietly. Its gravitational tides might perturb the Oort cloud, that icy graveyard of comets at our solar system's edge. Every 30 to 35 million years, as the Sun oscillates through the galactic plane, it could pass through this dark disk, triggering comet showers. Strikingly, Earth's extinction events, from the dinosaurs' demise to the lesser-known Triassic-Jurassic wipeout, show a rough match to this rhythm. Skeptics raise valid concerns. For one, the periodicity of extinctions is hotly debated. Some studies find statistical flaws in the pattern. Others question whether dark matter could clump into a disk at all. Ordinary matter collapses into disks because atoms collide, radiate energy, and slow down, but dark matter, by definition, doesn't interact like that. Unless, that is, it's not entirely collisionless. If just 5% of dark matter experiences weak interactions, a twist hinted at in some particle physics models, it could settle into a disk over billions of years. The hunt for evidence is as creative as the theory itself. Astronomers have scoured Gaia telescope data for stars wobbling under the dark disk's gravitational tug, while others simulate whether such a structure could survive the Milky Way's turbulent history. The most tantalizing clues might lie closer to home. If the dark disk exists, its gravity would subtly alter the orbits of planets and asteroids, an effect NASA space probes could potentially detect over decades of precision tracking. What makes this idea so captivating isn't just its potential to solve two mysteries at once, dark matter's nature and Earth's violent timeline, but its audacity to connect the cosmos's grandest scales to our planet's most pivotal moments. It's a reminder that the universe's hidden forces might not just shape galaxies, but the very story of life itself. Until we know for sure, the dark disk remains a ghostly what-if, lurking at the intersection of astrophysics and paleontology, waiting to be proven or forgotten. In 1998, two teams of astronomers made a discovery that would turn cosmology upside down. studying distant supernova, they expected to find the universe's expansion slowing down, a natural assumption, given gravity's relentless pull on everything from galaxies to dust clouds. Instead, they saw the opposite. The most far-off stellar explosions were dimmer than they should have been, meaning they were farther away than anyone had predicted. The universe wasn't just expanding, it was accelerating, as if some invisible force were stretching space itself apart faster and faster. This revelation was so shocking that team leader Saul Perlmutter initially suspected equipment errors. But the data held firm. The cosmos had a secret, and it would earn those scientists a Nobel Prize. The implications were staggering. For decades, the big question had been whether the universe would eventually collapse in a big crunch or fade into cold emptiness. Now, neither fate seemed certain. Something was overpowering gravity on the grandest scales, a mystery force dubbed dark energy. The term itself is a placeholder, a confession of how little we understand. Unlike dark matter, which pulls galaxies together, dark energy pushes them apart, acting like a kind of anti-gravity woven into the fabric of space, the most unsettling part. It makes up about 68% of the universe's total energy content, dwarfing both dark and ordinary matter combined. To grasp how bizarre this is, picture a ball tossed into the air. Normally, gravity would slow its ascent until it fell back down. But if that ball suddenly shot upward faster and faster, defying all logic, you'd know something strange was at work. That's exactly what supernova revealed. The light from these dying stars, billions of years old, showed space behaving in ways no existing theory could fully explain. Einstein's cosmological constant, a mathematical fudge he'd once called his greatest blunder, has suddenly found new life as a potential clue. Could dark energy be a property of empty space itself, growing stronger as the universe expands? The evidence didn't stop with supernova. Later studies of the cosmic microwave background, the afterglow of the Big Bang, showed space's geometry was flat, a finding that only made sense if dark energy filled the gaps. Even the large-scale structure of the universe, with its vast voids and galaxy filaments, seemed to bear dark energy's fingerprint, yet for all the indirect proof, its true nature remains elusive. Is it a new kind of energy field, like the inflationary force that birthed the cosmos? Or does it hint at a flaw in Einstein's gravity, requiring entirely new physics? What's certain is this: dark energy isn't just a footnote in cosmology. It's the dominant force shaping our universe's destiny, pushing galaxies apart so fiercely that, billions of years from now, distant star systems will vanish beyond an unreachable horizon. The discovery didn't just rewrite textbooks, it revealed how much we still don't know about the forces governing existence itself. And the deeper we look, the stranger the cosmos becomes. Einstein's greatest blunder might not have been a mistake after all, just a calculation off by a factor of 1 followed by 120 zeros. That's the staggering scale of the cosmological constant problem, a puzzle so profound it makes even seasoned physicists pause. The story begins in 1917, when Einstein introduced the cosmological constant to his equations of general relativity. At the time, the universe was thought to be static, and this mathematical tweak counteracted gravity's pull, preventing cosmic collapse. But when Hubble discovered the expanding universe, Einstein dismissed the constant as unnecessary. Decades later, dark energy's discovery resurrected it, only to reveal a discrepancy so vast it defies comprehension. Quantum field theory, our most successful framework for particle physics, predicts that empty space should seethe with energy. Every cubic centimeter of the vacuum ought to buzz with virtual particles popping in and out of existence, contributing to what's called vacuum energy. When you tally up these quantum fluctuations, the estimated energy density lands at around 10 to the power of 120 in Planck units. But here's the catch: observations of dark energy's effect, like the universe's accelerating expansion, require the cosmological constant to be 10 to the power of 120 times smaller. That's like expecting a mountain and finding a single grain of sand instead. This isn't just a rounding error. It's the worst mismatch between theory and observation in all of science. To make matters stranger, if the cosmological constant were even slightly larger, galaxies couldn't form, slightly smaller, and the universe would have collapsed long ago. The fine-tuning is so precise it feels engineered, sparking debates about multiverses or undiscovered symmetries that cancel out vacuum energy. Some theorists argue we've misunderstood quantum mechanics altogether, that vacuum energy might not gravitate the way we assume. Others propose exotic solutions, like extra dimensions siphoning off energy or dynamic fields that evolve over time. The cosmological constant problem cuts to the heart of physics' biggest challenge, unifying quantum mechanics and gravity. It's a reminder that dark energy isn't just a cosmic curiosity, it's a glaring signal that our understanding of reality is incomplete. Until we solve it, we're left staring at the universe's most unsettling question: why does nothing weigh so much and yet so little? The biggest question about dark energy isn't just what it is, it's whether it's always been the same. For decades, the lambda CDM model assumed dark energy was a constant force, represented by Einstein's cosmological constant, lambda. But what if it's not? What if dark energy evolves over time, growing stronger or weaker as the universe expands? The answer wouldn't just tweak our models, it would rewrite the cosmic forecast for everything that lies ahead. Take the evidence from Type Ia supernova, the same cosmic mile markers that first revealed dark energy's existence. While early studies pointed to a constant acceleration, newer observations, like those from the Dark Energy Survey, suggest subtle deviations. Some supernovae appear brighter or dimmer than lambda CDM predicts, as if dark energy's push wasn't perfectly uniform across cosmic history. It's like spotting footprints in the sand that suddenly change stride. Something might be altering its behavior. Then there's baryon acoustic oscillations, the frozen ripples from the early universe. These ancient sound waves, etched into the distribution of galaxies, act as a cosmic ruler. By measuring how their apparent size changes across different eras, astronomers can track how dark energy's influence has shifted. Recent surveys, like eBOS, hint that dark energy might have been slightly weaker in the universe's adolescence. The data isn't definitive, but it's enough to raise eyebrows, especially when paired with quirks in the cosmic microwave background. The Planck satellite's detailed maps of the Big Bang's afterglow show faint anomalies in how dark energy shapes large-scale structure, as if its grip loosened or tightened at key moments. The implications are staggering. If dark energy isn't constant, the universe's fate could swing between extremes. A strengthening dark energy might lead to the Big Rip, where galaxies, stars, and even atoms are torn apart in a runaway expansion. A weakening one could let gravity regain control, collapsing the cosmos in a fiery Big Crunch. And if dark energy fluctuates unpredictably, the universe might face a roller coaster of expansion and contraction with no clear endgame. Theories abound to explain these hints. Maybe dark energy isn't a static property of space but a dynamic field, like the inflaton that drove the Big Bang's exponential growth. Some models propose quintessence, a cosmic fluid that thins out or clumps over time. Others speculate about phantom energy, a hypothetical form that grows denser as space expands, accelerating the universe toward oblivion faster than light could keep up. For now, the data is too murky to crown a winner. Upcoming telescopes like the Vera Rubin Observatory and Euclid aim to settle the debate by mapping billions of galaxies across time. But the mere possibility that dark energy is in flux shakes cosmology to its core. It means the universe's expansion isn't just a one-way street. It's a story still being written with chapters we've only begun to read. Something doesn't add up in our cosmic calculations, and the discrepancy is growing wider with every new observation. Take the universe's expansion rate, known as the Hubble constant. For years, astronomers measured it two ways, by studying nearby supernova and the cosmic microwave background, the afterglow of the Big Bang. These methods should converge on the same number. Instead, they're diverging dramatically, with the gap now reaching 4 to 6 sigma, a chasm in statistical terms. This isn't just a rounding error. It's the Hubble tension, a full-blown crisis in cosmology that might force us to rewrite the rules of dark energy, gravity, or even the universe's very composition. Let's break down the clash. On one side, you have the late universe measurements. By tracking Type Ia supernova, standard candles with predictable brightness, teams like SH0ES and Pantheon Plus have pinned the Hubble constant at roughly 73 kilometers per second per megaparsec. That means for every million parsecs you move away from us, space itself stretches 73 kilometers faster every second. These supernova act like cosmic speedometers, calibrated by nearby Cepheid variable stars whose pulses reveal their true luminosity. The data is robust, refined over decades, and backed by independent methods like gravitational lensing of quasars. But then there's the early universe camp. Projects like Planck map the cosmic microwave background with exquisite precision, using slight temperature fluctuations to infer how fast the universe was expanding 13.8 billion years ago. Feed those primordial conditions into lambda CDM, our standard model of cosmology, and you'd expect today's Hubble constant to land around 67, a full 6 units lower than the supernova results. At first, scientists blamed measurement errors, but as instruments improved, the gap persisted. Even the James Webb Space Telescope, with its razor-sharp infrared eyes, recently confirmed the supernova readings, deepening the mystery. So what's behind the mismatch? One possibility is that dark energy isn't constant but evolving, subtly altering the expansion rate over eons. Imagine blowing up a balloon where the air pressure changes as it inflates, sometimes pushing harder, sometimes weaker. Alternatively, the early universe might have hidden ingredients like dark radiation or exotic neutrinos that tweak the cosmic microwave background snapshot. There's even a radical idea that dark matter interacts with itself more strongly than we thought, skewing how structures formed. The most thrilling and unsettling explanation is that our model of gravity is incomplete. Einstein's general relativity has passed every test thrown at it, from bending starlight to predicting gravitational waves. But what if it breaks down on cosmic scales? Modified gravity theories like emergent gravity or scalar tensor models attempt to explain the tension by tweaking how mass warps spacetime. None have yet dethroned lambda CDM, but the Hubble tension keeps them in the game. This isn't just academic quibbling. If the discrepancy is real, it implies the universe today is expanding faster than our theories predict, like a car accelerating without pressing the gas. Upcoming telescopes like the Vera Rubin Observatory and ESA's Euclid will map billions of galaxies to hunt for clues. Until then, the Hubble tension stands as a glaring crack in cosmology's foundation, reminding us that the cosmos still holds cards it hasn't revealed. Picture the universe's final act not with a whimper but with a scream. Galaxies ripped apart, stars shredded mid-orbit, planets disintegrating into cosmic dust. Even atoms torn asunder as space itself stretches faster than light can traverse it. This isn't science fiction. It's the Big Rip, an apocalyptic scenario where dark energy doesn't just accelerate the universe's expansion, but grows stronger over time, becoming so dominant that it overpowers every fundamental force holding reality together. The culprit, phantom energy, a hypothetical form of dark energy so extreme it defies our understanding of physics. The math behind this nightmare is deceptively simple. Ordinary dark energy, like Einstein's cosmological constant, maintains a steady density as the universe expands. but phantom energy's density increases, meaning its repulsive force snowballs as space grows. Imagine blowing up a balloon where each breath makes the rubber thinner and more volatile until pop, it can't hold itself together. In cosmic terms, this runaway effect would eventually overwhelm gravity's glue binding galaxies, then the electromagnetic force stitching molecules, and finally the strong nuclear force inside atoms. The universe wouldn't just fade into cold emptiness, it would violently unravel. But does the data support such a dramatic fate? Observations so far are ambiguous. The Planck satellite's measurements of the cosmic microwave background slightly favor quintessence, a milder form of evolving dark energy that weakens over time. Yet phantom energy isn't ruled out. Some supernova surveys show hints of dark energy's equation of state, a key parameter describing its pressure-to-density ratio dipping below -1, the threshold for phantom behavior. These measurements sit on the knife's edge of uncertainty, though with error bars still too wide to confirm anything, the stakes couldn't be higher. If phantom energy exists, the countdown to the Big Rip depends on just how fast its density grows. Conservative estimates place the event trillions of years in the future, long after stars burn out and black holes evaporate. But if phantom energy is more aggressive, the end could arrive in as little as 22 billion years, a blink in cosmic time. For comparison, Earth's oceans would boil off in just 300 million years as phantom energy's grip distorts the solar system's delicate balance. Skeptics argue that phantom energy violates energy conditions central to general relativity, potentially leading to paradoxes like negative kinetic energy or causality-breaking wormholes. Others counter that quantum fields in the early universe exhibited similar behavior during inflation, a period of exponential expansion, so the laws of physics might accommodate phantom energy after all. The truth might lie in upcoming experiments. The Vera Rubin Observatory's decade-long legacy survey of space and time could spot subtle changes in dark energy's push over billions of years, while NASA's Nancy Grace Roman Space Telescope will hunt for phantom energy's fingerprints in the bending of light around galaxy clusters. What makes phantom energy so haunting isn't just its destructive potential, it's the way it exposes how fragile our cosmic assumptions are. The universe's fate hinges on a number we've barely begun to measure, hiding in the dim light of dying stars. Whether the Big Rip remains a theoretical specter or an inevitable certainty, one thing is clear: dark energy's true nature is stranger and potentially more violent than we ever dared imagine. The cosmological constant is the simplest answer to dark energy, a static, unchanging force woven into the fabric of space itself. But what if the truth isn't so tidy? Enter quintessence, a radical alternative that paints dark energy as a dynamic, evolving field, one that ebbs and flows over cosmic time. Unlike the rigid predictability of Einstein's constant, quintessence breathes life into dark energy, suggesting it could have been stronger in the past, weaker in the future, or even switch directions entirely. Think of it like this: the cosmological constant is a frozen river, fixed and unyielding, while quintessence is a living current, shifting with the universe's expansion. This isn't just philosophical, it's a real, testable difference that could redefine the cosmos's fate. For instance, if quintessence weakens over time, gravity might eventually regain control, pulling the universe back into a big crunch. If it strengthens, we could face a Big Rip scenario where galaxies, stars, and even atoms are torn apart. Or it could oscillate, creating cycles of expansion and contraction, a cosmic heartbeat echoing across eternity. The challenge is catching quintessence in the act. Unlike the cosmological constant, which leaves a uniform fingerprint, a dynamic field would imprint subtle variations in how galaxies cluster and how light bends across the universe. That's where telescopes like Euclid come in. Launching in the next few years, Euclid will map billions of galaxies across 10 billion light-years, hunting for tiny deviations in their distribution, clues that dark energy's push isn't perfectly steady. By measuring the clumpiness of the universe at different epochs, Euclid could spot quintessence's signature, a gradual shift in how dark energy sculpts the cosmos over time. Other projects are joining the chase. The Vera Rubin Observatory's legacy survey of space and time will track supernova with unprecedented precision, watching for telltale brightness variations that betray dark energy's changing strength. Meanwhile, the Dark Energy Spectroscopic Instrument DESI is cataloging millions of quasars, using their light to probe expansion rates across cosmic history. Together, these missions form a net tightening around quintessence's elusive behavior. Yet the mystery runs deeper. Some theorists propose that quintessence isn't even a single field but a tapestry of interacting forces, like cosmic weather systems colliding in the void. Others suggest it might couple with dark matter, creating feedback loops that alter the universe's expansion in unpredictable ways. The possibilities are as vast as they are speculative, but that's the thrill of the hunt. Whether quintessence is real or not, the search pushes cosmology to its limits, forcing us to ask not just what dark energy is, but whether it's always been the same, and what that means for the story we tell about everything. Here's something strange to wrap your head around. Dark energy didn't always dominate the universe. For billions of years after the Big Bang, gravity reigned supreme, pulling matter together into galaxies and galaxy clusters. Dark energy existed, but it was a background player, its repulsive force too weak to compete with gravity's grip. Then, around 5 billion years ago, something flipped. As the universe expanded and matter spread thinner, dark energy's push suddenly took over, accelerating cosmic expansion. Why then? Why not sooner or later? This is the coincidence problem, and it's one of the most perplexing wrinkles in modern cosmology. Think of it like a seesaw balanced at just the right moment. Dark energy's rise to power coincides almost exactly with the era when complex life became possible. Stars had forged heavy elements, planets had formed, Earth had cooled. If dark energy had dominated earlier, galaxies wouldn't have had time to assemble, leaving the universe a dark, empty void. If it had kicked in later, the cosmic density might have already triggered a big crunch, collapsing everything before life could emerge. The timing feels uncannily precise, as if the universe knew we'd be here to notice. This eerie alignment has led some scientists to consider the anthropic principle, the idea that the universe's fundamental constants are what they are because, well, we're here to observe them. In other words, if dark energy hadn't emerged at this Goldilocks moment, no one would exist to wonder about it. It's a controversial stance, less an explanation than a philosophical shrug, but it opens the door to wilder possibilities. Could our universe be one of countless others in a multiverse, each with different dark energy strengths? Most might be sterile, devoid of galaxies or life, while ours just happens to have the right conditions for observers. The multiverse angle isn't just speculative fantasy. Certain theories, like eternal inflation, suggest new universes constantly bubble into existence, each with random physical laws. In most, dark energy's strength might be too weak to matter or so strong it tears space apart instantly. Ours landed in the vanishingly rare sweet spot. String theory lends some credence to this, with its landscape of possible universes, each defined by different configurations of extra dimensions. Still, critics argue this just kicks the can down the road. Even if a multiverse exists, why does our corner of it obey such suspiciously life-friendly rules? Alternative explanations try to ground the coincidence in physics. Some models propose dark energy isn't constant but tied to the density of matter, activating only when the universe reaches a specific threshold of expansion. Others suggest it's a phase transition like water freezing into ice, where the properties of space itself shift under the right conditions. There's even a radical idea that dark energy interacts with time, growing stronger as the universe ages. But so far, none of these theories have definitive evidence to back them. The coincidence problem gnaws at cosmology because it hints at something deeper. Our models might be missing a crucial link between dark energy and cosmic evolution. Future telescopes, like the European Space Agency's Euclid mission, could hunt for clues in the distribution of galaxies across time, searching for signs that dark energy's rise wasn't just a fluke but part of a grander, unseen mechanism. Until then, we're left staring at the universe's timeline, wondering if the most important turning point in cosmic history was mere luck or something far more deliberate. What if the speeding galaxies and runaway expansion of the universe aren't being pushed by dark energy, but pulled by gravity itself behaving differently than we thought? This radical idea turns cosmology on its head, suggesting Einstein's theory of general relativity, while flawless in our solar system, might falter on the grandest scales. Instead of invoking an invisible force stretching space apart, modified gravity theories propose we've simply misunderstood how mass warps spacetime when galaxies and voids span billions of light years. Take modified Newtonian dynamics, the most famous challenger, proposed in the 1980s by physicist Mordechai Milgrom. Noticed something peculiar about galaxy rotation curves. Just like Vera Rubin's dark matter revelations, Milgrom saw stars orbiting galaxies too fast for the visible mass to explain. But rather than adding invisible matter, he tweaked Newton's second law. When gravitational acceleration drops below a certain threshold, it weakens less than expected. Suddenly, galaxy rotations made sense without dark matter's extra pull. The appeal lies in its simplicity: no mysterious particles, just a subtle adjustment to gravity's rules where it's weakest. Yet the cosmos doesn't give up its secrets easily. While excels at galaxy-scale puzzles, it stumbles elsewhere. The bullet cluster's separated mass and gas, for instance, still demand some form of invisible matter. Then there's the cosmic microwave background's intricate patterns, which dark matter models nail with eerie precision. Struggles to replicate these without bolting on extra assumptions, diluting its elegance. Even Milgrom admits his theory can't fully replace dark matter. At best, it might explain part of the mystery. More sophisticated theories aim higher. Tensor vector scalar gravity, or TVS, adds layers to attempting to reconcile it with relativity. Others, like emergent gravity, suggest gravity isn't a fundamental force but a side effect of entropy, like thermodynamics emerging from atoms' chaos. These ideas flirt with profound truths but often lack the predictive power of lambda CDM. When the Hubble tension revealed discrepancies in cosmic expansion rates, modified gravity seized the moment, offering tweaks to relativity that might bridge the gap. Yet no single alternative cleanly explains everything from galaxy rotations to colliding clusters. The real tension isn't just between theories, it's in philosophy. Modified gravity appeals to those who distrust the universe being 95% invisible. Why invent dark matter and dark energy, they argue, when we might just have the math wrong? But Occam's razor cuts both ways. Adding new particles keeps gravity's equations pristine, while modifying them risks unraveling physics' most rigorously tested framework. It's the ultimate tug of war between simplicity and completeness. Future experiments could tip the scales. If telescopes like Euclid or the Vera Rubin Observatory find subtle deviations in how light bends around galaxy clusters, hints that gravity's grip weakens or strengthens unexpectedly, modified gravity might gain ground. Until then, the debate rages on, a reminder that even Einstein's towering legacy isn't beyond questioning. After all, science advances not by clinging to dogma, but by daring to ask, what if we've missed something fundamental? Among the most unsettling possibilities in modern physics is the idea that dark energy could be a ticking time bomb, not just stretching the universe apart, but rewriting the very laws of reality in an instant. This nightmare scenario, known as vacuum decay, hinges on a bizarre property of quantum fields, the notion that what we call empty space isn't truly empty but simmering with potential energy. If this vacuum state is only temporarily stable, a false equilibrium, then a single quantum fluctuation could unleash a bubble of true vacuum, where the fundamental constants we rely on, like the speed of light or the strength of gravity, no longer apply. And once triggered, this bubble would expand at light speed, erasing everything in its path before any observer could even blink. The math behind this doomsday comes straight from particle physics. The Higgs field, which gives particles their mass, exists in a precarious balance, like a marble resting in a shallow valley. It's stable for now, but if a deeper valley exists, a lower energy state, the marble could suddenly roll downhill and the Higgs value would shift catastrophically. In that new state, atoms might not hold together, chemistry would cease to function, and the universe as we know it would vanish. Dark energy enters the picture because its repulsive force could make the universe's current vacuum state even more unstable. Think of it like stretching a rubber sheet. The tension might push the marble closer to the edge of that valley, increasing the odds of a catastrophic slip. But how likely is this? Physicists estimate our vacuum's lifetime to be astronomically long, potentially longer than the current age of the universe. Particle colliders like the Large Hadron Collider have probed the Higgs field stability, and so far it seems we're safely in that shallow valley. Yet the uncertainty isn't zero. If dark energy's strength changes over time, or if exotic high-energy processes occur in deep space, the odds could shift. Some theories even suggest that vacuum decay might have already been triggered elsewhere in the cosmos, with a death bubble racing toward us right now, though we'd have no way to know until it arrived. Thankfully, there's a silver lining. The sheer scale of cosmic time means vacuum decay is overwhelmingly improbable on human timescales, and if it did happen, the end would be so swift and total that there'd be no pain, no warning, just an instantaneous rewrite of existence. Still, the fact that such an event is even conceivable forces us to confront a humbling truth. The universe's foundations might be more fragile than they appear, and dark energy could hold the keys to far more than just expansion. It's a reminder that for all our knowledge, we're still guests in a cosmos full of unimaginable power and mystery. What if everything we think we know about dark energy is just a cosmic illusion, a trick of perspective caused by where we happen to sit in the universe? This is the startling premise of the void hypothesis, a radical idea suggesting we might be living in an unusually empty pocket of space, making the rest of the universe appear to accelerate away from us when it's actually business as usual. Imagine standing alone in a vast, dimly lit room, watching shadows on the walls stretch and distort. If you didn't know the room was mostly empty, you might assume the walls themselves were moving. That's the essence of this theory. Our local void could be fooling us into inventing dark energy to explain observations that don't require it at all. The math behind this isn't science fiction. If Earth occupied the center of a gigantic underdense region, a bubble hundreds of millions of light years wide with far fewer galaxies than average, the gravitational dynamics would shift. Matter outside the void would pull harder on us than the sparse matter inside, creating an apparent outward push. Cosmologists call this the Hubble bubble scenario. In principle, it could mimic dark energy's signature, distant supernova appearing dimmer because space within the void expands slightly faster than the denser universe beyond. Early studies even found tentative evidence for such a structure, with galaxy surveys showing peculiar dips in density around our cosmic neighborhood. But here's the catch. For this illusion to hold, the void would need to be staggeringly large, nearly impossible under standard cosmology's odds. The cosmic microwave background, our snapshot of the infant universe, reveals a remarkably uniform distribution of matter. A void big enough to mimic dark energy would require Earth to sit at its exact center, a coincidence so improbable it makes physicists shudder. Statistically, we'd expect to find ourselves in a typical region, not a privileged position akin to the pre-Copernican belief that Earth was the universe's focal point. The void hypothesis also struggles to explain other dark energy clues. The cosmic microwave background's detailed fluctuations, the large-scale distribution of galaxies, and the timing of when cosmic acceleration began all align with dark energy's uniform push, not a local anomaly. Even the most carefully tuned voids can't reproduce all these observations simultaneously without introducing new inconsistencies. That's why most cosmologists consider the idea a creative but ultimately unconvincing workaround, like trying to fix a leaky boat by redesigning the ocean. Still, the possibility lingers because science thrives on skepticism. Some researchers continue to explore refined void models, imagining scenarios where multiple smaller voids overlap, or where unusual initial conditions in the early universe left behind a rare density dip. Others propose hybrid theories where a modest void amplifies dark energy's effects, blending both ideas into a compromise. But until someone discovers a void vast enough to challenge the mountain of evidence for dark energy, or until new physics upends our understanding of cosmic structure, the universe's accelerating expansion remains best explained by the enigmatic force we call dark energy. The void hypothesis isn't just a fringe idea, it's a stress test for cosmology itself. It forces us to question how well we truly know the universe's shape and our place within it. And while the evidence overwhelmingly points away from this cosmic mirage, its mere existence reminds us that even the most settled theories deserve scrutiny, because sometimes the most profound truths hide in the gaps between what we see and what we assume. Dark matter doesn't just lurk in the shadows of the cosmos, it's the invisible architect of everything we see. Without its gravitational pull, galaxies as we know them wouldn't exist. Picture the early universe, a swirling soup of gas and particles, far too hot and chaotic for stars to form. Ordinary matter alone couldn't overcome this turbulence, but dark matter's gravity acted like a cosmic scaffold, creating dense pockets where gas could cool and collapse. These pockets became the seeds of the first galaxies, anchored by halos of dark matter so massive they bent the fabric of space itself. This isn't just theory. Simulations like Illustris have recreated the universe's evolution with stunning accuracy, tracing how dark matter's distribution shaped the cosmic web. The results are mesmerizing, vast, thread-like filaments of dark matter stretching across billions of light years, intersecting at nodes where galaxies cluster like pearls on a string. Ordinary matter simply followed these invisible blueprints, flowing into the gravitational wells dark matter carved out. You can see its fingerprints everywhere in the way spiral galaxies rotate too fast for their visible mass, or how galaxy clusters bend light around them like cosmic lenses. But dark matter's role isn't just about brute force. Its distribution holds clues to the universe's quirks. Take dwarf galaxies which orbit larger ones like the Milky Way. Simulations predict thousands should exist, each cradled in its own dark matter halo. Yet we've found only a fraction, and their dark matter content varies wildly. Some are nearly pure dark matter, while others seem to have none at all. This diversity problem hints that dark matter might interact in ways we don't yet understand, or that our models miss key physics at small scales. The cosmic web structure reveals even deeper mysteries. Dark matter doesn't clump uniformly. Its filaments weave a delicate balance between gravity's pull and the universe's expansion. In some regions, halos merge violently, birthing colossal galaxy clusters. In others, dark matter's faint tug leaves behind vast voids, empty deserts where galaxies are eerily absent. The Illustris simulations show this dance in exquisite detail, matching real-world observations so precisely they've become a virtual testing ground for cosmology. Yet for all its power, dark matter remains frustratingly elusive. We can map its gravitational shadows, but its true nature defies detection. Is it a single type of particle or a menagerie of unseen substances? Does it interact with itself or only through gravity? Each simulation that nails one aspect of galaxy formation seems to uncover new puzzles elsewhere. One thing's certain, without dark matter's hidden hand, the universe would be a vastly emptier, darker place devoid of the galaxies, stars, and planets that make the cosmos alive. Its silence is what lets the universe sing. Right now, dark energy makes up about 68% of the universe's energy budget, but that number is growing. As space itself continues to expand, dark energy's density remains constant, meaning its influence grows stronger relative to matter, which dilutes over time. In the distant future, this relentless acceleration will rewrite the fate of everything we see. Picture a universe where galaxies aren't just drifting apart but being dragged away by an invisible tide, their light stretched beyond detection, their stars left to burn out in isolation. This is the Big Freeze, the slow, silent death of the cosmos as dark energy turns it into an ever-expanding graveyard of scattered embers. The timeline for this dissolution is almost beyond comprehension. Tens of billions of years from now, the Milky Way and Andromeda will have long since merged into a single aging galaxy, their stars dimming as fuel runs low. At first, neighboring galaxy clusters will still be visible, bound by gravity's grip. But as dark energy's push intensifies, even these titanic structures will be torn apart. Around 100 billion years from now, any galaxies beyond our local group will redshift into invisibility, their light stretched so far that not even the most advanced telescopes could spot them. The universe will appear empty, as if we're the last island in an endless, darkening sea. But the real chilling twist comes later. As expansion accelerates exponentially, even the bonds holding galaxies together will fail. First, the outer stars will be stripped away, flung into the void. Then, over trillions of years, stellar orbits will destabilize and planets will detach from their stars. Eventually, the protons and neutrons composing matter itself might decay, reducing stars and planets to faint clouds of subatomic particles. The last black holes, after swallowing the remnants of galaxies, will evaporate via Hawking radiation, leaving behind only a thin haze of photons too weak to detect. The cosmos will reach maximum entropy, a state where no energy can be extracted, no work can be done, and no structure remains. It's the ultimate heat death where time loses all meaning. Yet some theories offer a dramatic counterpoint, the cyclical universe. Instead of fading into eternal stillness, the cosmos might rebound in an endless cycle of expansion and contraction. In these models, dark energy isn't constant but fluctuates, eventually reversing into a force of attraction. The universe would collapse back into a singularity, a big crunch, which then triggers another big bang. This idea, rooted in certain string theory and quantum gravity models, suggests our universe could be one page in an infinite cosmic book, with each chapter starting anew. The appeal is obvious. It dodges the bleak finality of heat death, offering immortality through rebirth. There's even a wilder variation, the Big Bounce. Here, the universe avoids total collapse by reaching a minimum size where quantum effects take over, bouncing back like a compressed spring. Recent work in loop quantum gravity hints this might be possible, with space-time itself having a granular structure that prevents true singularity. If true, the cosmos could be timeless, cycling through expansions and contractions forever, with dark energy merely one phase in an eternal rhythm, but evidence remains thin. Observations overwhelmingly support dark energy's dominance, with no signs yet of a slowdown that would herald a cyclical reversal. The universe's flat geometry also suggests total collapse is unlikely unless dark energy's properties change dramatically. Still, the mere possibility keeps the debate alive, a reminder that our understanding of cosmic fate is still evolving. Whether the universe ends in ice or fire, darkness or renewal, one thing's certain: dark energy holds the keys to the cosmos's ultimate destiny, and we've only just begun to glimpse its power. Something strange is happening at the edge of our cosmic map, an anomaly so perplexing it challenges the very notion of what lies beyond the observable universe. It's called dark flow, a mysterious, uniform drift of galaxy clusters moving en masse toward a single point in the distant cosmos, as if pulled by an invisible hand. These aren't random motions. Hundreds of clusters, some billions of light-years apart, are streaming in the same direction at baffling speeds, over 600 miles per second, defying the expected expansion of space. The first hints emerged in 2008 when astronomers studying the cosmic microwave background spotted subtle temperature shifts in the afterglow of the Big Bang, suggesting entire superclusters were being tugged toward something unimaginably vast. The leading explanation, a gravitational titan lurking outside our observable universe, perhaps a colossal structure left over from the chaotic pre-Big Bang era, or even the gravitational pull of another universe entirely. Imagine dropping leaves into a river and watching them all drift toward an unseen waterfall just beyond the horizon. That's the scale of this mystery. The cluster's motion aligns toward the constellations Centaurus and Hydra, but the source itself remains hidden by the cosmic veil, lying so far away its light hasn't had time to reach us in 13.8 billion years. Skeptics argue dark flow could be an artifact of measurement errors or local density variations, yet repeated studies, including data from the Planck satellite, have only sharpened the anomaly. When researchers subtracted all known gravitational influences, the Milky Way's motion, the pull of nearby superclusters, the flow persisted, unmoved. Even more startling, the effect seems coherent across distances that should be causally disconnected. Regions of space too far apart to influence each other since the Big Bang are moving in eerie unison. This raises electrifying possibilities. If the flow is real, it might hint at a multiverse where our universe is one bubble among countless others in an infinite cosmic foam. The gravitational tug of a neighboring universe could theoretically reach across the void, warping our spacetime like the moon's pull distorts the ocean. Alternatively, the flow might trace back to exotic pre-Big Bang physics, a relic of quantum fluctuations or black holes from a prior cosmic cycle, imprinting their influence on our newborn universe. For now, dark flow remains one of cosmology's most contentious puzzles. Upcoming missions like the European Space Agency's Euclid telescope could settle the debate by mapping galaxy motions with unprecedented precision. Until then, this ghostly current serves as a humbling reminder. The universe's greatest mysteries might not lie in what we can see, but in the unseen forces shaping everything from beyond the edges of our known reality. What if dark matter and dark energy aren't separate entities at all, but two faces of the same cosmic enigma? This tantalizing possibility has led physicists to hunt for a unified theory, a single exotic substance that could explain both the invisible glue holding galaxies together and the mysterious force ripping the universe apart. One of the most audacious contenders is Chaplain gas, a hypothetical fluid that bizarrely shifts its behavior over cosmic time. In the early universe, it would have clustered like dark matter, anchoring galaxies with its gravitational pull. But as space expanded, the gas would thin out and take on dark energy's repulsive properties, accelerating the universe's expansion. It's a cosmic chameleon, morphing to fit the needs of each era, elegant but perhaps too convenient. The math behind Chaplain gas hinges on its unusual equation of state, which allows its pressure to drop as its density decreases, a stark contrast to ordinary fluids. Early enthusiasm for the idea waned when astronomers realized it struggled to explain the universe's large-scale structure. While it could mimic dark matter's clumping or dark energy's push, doing both simultaneously proved messy. Observations of galaxy clustering and the cosmic microwave background revealed inconsistencies, like suppressed growth of cosmic filaments that should have formed more robustly. Worse, Chaplain gas predicts a specific sound speed for density waves in the early universe, one that clashes with the patterns etched into the oldest light we can see. Then there's K-essence, short for kinetic essence, a dynamic field theorized to permeate space, its energy density shifting based on how it interacts with itself. Unlike Chaplain gas, K-essence doesn't try to be everything at once. Instead, it proposes that dark matter and dark energy arise from the same fields evolving kinetic energy, like a pendulum swinging between two regimes. In high-density regions like galaxy clusters, the field's kinetic energy would behave like a pressureless fluid dark matter. In the void between galaxies, it would transform into a cosmic accelerator, dark energy. The appeal here is flexibility. K-essence can be tuned to fit a range of observations by adjusting how its kinetic terms evolve. Yet K-essence faces its own hurdles. For one, it requires fine-tuning to match the observed balance between dark matter and dark energy today. The field's transition from clumping to accelerating must happen at precisely the right moment to align with supernova data and galaxy surveys, a coincidence nearly as puzzling as the one it's trying to solve. There's also the problem of phantom energy. Some K-essence models inadvertently predict a future big rip, where the field's energy density grows infinite, tearing apart spacetime itself. While dramatic, this scenario isn't supported by current observations, leaving theorists to stitch together convoluted corrections. The quest for unification doesn't stop there. Other ideas like quartessence or scalar tensor theories weave dark matter and dark energy into modified gravity frameworks, often at the cost of mathematical complexity. Some models introduce extra dimensions or exotic particles that blur the line between the two phenomena. But here's the sticking point: none of these theories have delivered a knockout punch. Each can explain certain observations, but none seamlessly reconcile all the data. From galaxy rotation curves to the cosmic microwave background's fine details without introducing new contradictions. Part of the challenge is the sheer breadth of evidence to cover. Dark matter's fingerprints are everywhere, in the way galaxies spin, how clusters collide, and how light bends around massive objects. Dark energy's signature, meanwhile, is etched into the universe's accelerating expansion and the spacing of galaxy superclusters. A successful unified theory must account for all these clues without breaking what we already know. It's like assembling a jigsaw puzzle where half the pieces are hidden and the picture keeps changing. For now, the Lambda CDM model, with its separate dark matter and dark energy components, remains the best fit despite its gaps. Unified theories aren't dismissed, they're just not yet compelling enough to overthrow the standard view. But the search continues, driven by the hunch that the universe's greatest mysteries might share a common origin. Whether the answer lies in Chaplain gas, K-essence, or something even stranger, one thing's certain: the interplay between dark matter and dark energy is far more intricate than we ever imagined, and the final chapter of this cosmic saga has yet to be written. Imagine if the universe had a preferred direction, a cosmic axis that defied one of cosmology's most sacred principles, the idea that space should look the same in all directions. That's the unsettling puzzle at the heart of the so-called axis of evil, a bizarre pattern buried in the cosmic microwave background, the oldest light in the universe. When scientists first mapped this faint afterglow of the Big Bang, they expected a random scatter of hot and cold spots like static on an old TV. Instead, they found something hauntingly ordered. Some of the largest fluctuations align eerily with the plane of our solar system, as if the universe itself were whispering that we occupy a special place, a notion modern astronomy has spent centuries trying to erase. This anomaly got its ominous nickname not for any malevolence, but because it threatens to upend our assumptions. If the alignment is real, it could mean the universe isn't as isotropic or uniform in all directions as we thought. One explanation points to a primordial flaw in the fabric of spacetime, a relic from before inflation, the hypothetical burst of exponential expansion that ironed out the universe's wrinkles. Perhaps inflation didn't erase all traces of the pre-Big Bang chaos, leaving behind a faint directional imprint like a scar. Others suggest the alignment might be evidence of a multiversal tug, where neighboring universes in a vast multiverse exert subtle gravitational pulls on our own, warping the cosmic microwave background in detectable ways. But skepticism runs deep. Critics argue the axis could be an illusion, an artifact of our limited vantage point. The cosmic microwave background is filtered through the Milky Way's gas and dust, which might introduce biases. Even the motion of our solar system through space creates a dipole effect, like the Doppler shift of a siren as it passes, which could skew the data. When researchers subtracted these local influences, the signal persisted, but its statistical significance wobbled. Some analyses dismiss it as a fluke of cosmic variance, the universe's natural lumpiness, while others insist the alignment is too pronounced to ignore. The stakes are high. If the axis reflects a fundamental anisotropy, dark energy models might need recalibrating. A directional universe could mean dark energy's strength varies across space, challenging the cosmological principle that underpins everything from galaxy formation to the expansion rate. Alternatively, if the axis stems from pre-inflationary physics, it might hint at exotic fields or dimensions that shaped the early universe's structure before inflation reset the clock. Either way, the anomaly lingers like a crack in cosmology's foundation, a reminder that the universe's greatest mysteries often hide in plain sight, written in the faintest light of all. Deep in the constellation Boötes lies a cosmic ghost town, a void so vast and empty it defies everything we know about the universe's structure. Spanning 330 million light-years, the Boötes void is a yawning chasm of near-nothingness, where astronomers expected to find thousands of galaxies but have counted fewer than 60. To put that in perspective, a typical region of space this size would host around 2,000 galaxies. Instead, this void is a staggering desert, a place where dark energy's repulsive push seems to have cleared the stage with ruthless efficiency. Voids like Boötes aren't just empty patches, they're cosmic laboratories for dark energy's most dramatic effects. In these regions where matter is vanishingly sparse, dark energy dominates unchallenged. Without galaxies or clusters to anchor space with gravity, the void expands faster than its surroundings, stretching the fabric of reality itself. Imagine blowing up a balloon with a weak spot. As the rubber stretches, the thin area bulges outward faster than the rest. That's the Boötes void, a runaway expansion zone where dark energy's influence is magnified, offering clues to how it behaves in the absence of competing forces. But the mystery runs deeper than just emptiness. Voids like Boötes flout our expectations of how structure forms in the universe. According to simulations, tiny quantum fluctuations in the early universe should have seeded some galaxies here, even if fewer than average. Yet Boötes is emptier than the math predicts, as if something, or someone swept it clean. One theory suggests primordial dark energy fluctuations might have suppressed matter clustering in these regions, leaving behind exaggerated voids. Another idea posits that supervoids like Boötes could be overlapping bubbles, where multiple smaller voids merged over billions of years, amplifying the effect. The real enigma is what voids reveal about dark energy's distribution. Is it perfectly uniform, as the cosmological constant suggests, or does it clump subtly, stronger in voids and weaker in galaxy clusters? Observations of distant supernova in voids show slight deviations in brightness, hinting that dark energy's repulsive force might vary ever so slightly across space. If confirmed, this could upend our simplest models, suggesting dark energy isn't a static backdrop but a dynamic player that shifts with the cosmic environment. Then there's the eerie cold spot in the cosmic microwave background, a frigid patch that some physicists speculate could be the shadow of a supervoid even larger than Boötes. If true, it would mean voids aren't just local oddities but titanic structures shaping the universe's large-scale geometry. Their gravitational pull, or rather, their lack of it, can divert light from the cosmic microwave background, leaving telltale imprints. These ghostly fingerprints might hold the key to understanding whether dark energy's strength fluctuates across the cosmos, or if it's as unchanging as the vacuum of space itself. For all their emptiness, voids like Boötes are anything but barren of meaning. They're extreme experiments in how dark energy sculpts the universe, testing the limits of our theories. In their vast, silent depths, the rules of cosmology stretch thin, and the answers we find might rewrite them entirely. The quantum realm might hold the key to dark matter's deepest secrets, not in the particles we've already discovered, but in the shadowy corners of physics we've yet to explore. Imagine if dark matter isn't just a heavier version of ordinary matter, but a fundamental piece of a grander puzzle, one that ties together gravity and quantum mechanics in ways we've never imagined. This is where theories like supersymmetry enter the stage, proposing that every known particle has a hidden, heavier superpartner. Among these could be the neutralino, a hypothetical particle that doesn't interact with light yet exerts gravitational pull. If real, it would elegantly solve two problems at once, explaining dark matter's elusive nature and filling gaps in the standard model of particle physics. But supersymmetry isn't the only contender. Sterile neutrinos, ghostly particles that barely interact with anything at all, could also lurk in the quantum shadows, their sheer abundance shaping the cosmos invisibly. Then there's the mind-bending possibility that dark matter isn't confined to our familiar three dimensions. String theory suggests extraspatial dimensions curled up at scales too tiny to detect, and dark matter might be a vibration in these hidden folds of reality. Picture a universe where gravity leaks into these dimensions, explaining why it feels so weak compared to other forces. In this scenario, dark matter particles could be higher dimensional entities whose gravity bleeds into our world, tugging on galaxies without ever fully revealing themselves. It's a radical idea, but one that could bridge the chasm between quantum physics and cosmology, if we could ever find evidence. The most tantalizing clue might come from quantum gravity itself. Theories like loop quantum gravity propose that space-time has a granular structure at the smallest scales, and dark matter could be a manifestation of these quantum atoms of space. Alternatively, some models suggest dark matter interacts through an unknown quantum field, subtly altering the fabric of reality in ways we're only beginning to model. Experiments hunting for quantum fluctuations in empty space or anomalies in gravitational waves might one day stumble upon dark matter's signature hidden in the noise. What makes these theories so compelling isn't just their audacity, it's their potential to solve multiple mysteries at once. A quantum origin for dark matter could explain why it's so pervasive yet so aloof, why it shapes galaxies but ignores light, and why it seems to dance just beyond the edge of our detectors. Until we peer deeper into the quantum abyss, dark matter's true nature remains one of physics' greatest unfinished equations, a riddle written in the invisible ink of the cosmos itself. Black holes have long been considered the universe's ultimate survivors, cosmic monsters so powerful that not even light can escape their grasp. But even these titans may not be immune to dark energy's ruthless expansion. Picture a future so distant it defies imagination. Trillions of years from now, as galaxies are ripped apart and stars vanish into the void, black holes will find themselves stranded in an ever-expanding emptiness, cut off from the gas, dust, and stars they once devoured. This is the beginning of the end for even the most formidable structures in the cosmos. As dark energy accelerates the universe's expansion, the space between galaxies stretches faster and faster, eventually isolating every object beyond reach. For black holes, this means no new material to feed on, no swirling accretion disks to sustain them. They'll become dark, dormant relics, their growth stunted by the sheer emptiness around them. But their fate gets even stranger. Without incoming matter to counteract the process, they'll slowly shrink, thanks to a phenomenon predicted by Stephen Hawking in the 1970s, Hawking radiation. At the quantum level, virtual particles constantly pop in and out of existence near a black hole's event horizon. Occasionally, one particle falls in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over incomprehensible stretches of time, this drip-fed evaporation will cause even the most massive black holes to fade away, their energy dissipating into the cold, dark cosmos. The timeline for this cosmic decay is staggering. A black hole with the mass of our Sun would take around 10 to the power of 67 years to fully evaporate, a number so vast it dwarfs the current age of the universe billions of times over. Supermassive black holes like the one at the Milky Way's core would persist even longer, perhaps 10 to the power of 100 years. But in a universe dominated by dark energy, time is the one resource no object can escape. Eventually, even these last bastions of structure will dissolve into a faint mist of particles, leaving behind a void so empty that not even the memory of their existence remains. This bleak scenario, known as the black hole era, is just one chapter in the universe's slow march toward maximum entropy, a state where no energy gradients remain and nothing can ever change again. But here's the twist. Some theories suggest that Hawking radiation might not be the final word. Quantum gravity models hint that black holes could leave behind microscopic remnants, indestructible nuggets of information encoding their entire history. These hypothetical quantum fossils might outlast even the heat death of the universe, drifting eternally through the darkness like silent witnesses to a cosmos long gone. Yet for all its inevitability, the black hole era also underscores the delicate balance that defines our universe. The fact that black holes can exist at all, let alone dominate galaxies for billions of years, relies on a precise interplay between gravity, quantum mechanics, and the expansion of space. Dark energy's ultimate victory isn't just about emptiness. It's a reminder that even the most permanent-seeming structures are temporary in the grand scheme of time. And as the last black holes flicker out, they'll mark the end of an era that began with the Big Bang, leaving behind a universe so alien, so unrecognizable, that it challenges our very understanding of reality itself. We tend to think of the Big Bang as a single, explosive beginning, but what if it wasn't alone? Emerging theories suggest our universe's birth might have been accompanied by a shadowy counterpart, a dark Big Bang, where dark matter and dark energy emerged from their own separate genesis. While conventional models treat dark sectors as passive players in cosmic inflation, some physicists now speculate they could have been the very trigger that set everything in motion. Imagine a cosmic double birth, where the visible universe we know unfurled alongside a hidden counterpart, each with its own distinct rules and rhythms. The standard inflation narrative describes a fleeting moment when space expanded exponentially, smoothing the universe into the relatively even fabric we see today. But here's the puzzle. What catalyzed this hyper-expansion? One provocative idea posits that dark energy, or an early ancestor of it, was the hidden hand behind inflation. In this scenario, a primordial form of dark energy, far denser than today's version, flooded the infant universe, stretching it like taffy in a fraction of a second. As this energy decayed, it might have seeded not only the visible cosmos but also the dark matter that would later glue galaxies together. It's a poetic symmetry. The same force now ripping the universe apart could have been responsible for its initial coherence. Meanwhile, the dark Big Bang hypothesis takes this even further. Proposed in recent studies, it suggests dark matter didn't passively condense from the same primordial soup as ordinary matter. Instead, it might have arisen from a separate, delayed phase transition, a second bang occurring microseconds or even years after the initial one. This could explain why dark matter vastly outweighs visible matter without overproducing certain particles predicted by conventional models. Think of it like two orchestras tuning up at slightly different times. One plays the melody of stars and planets, while the other hums the bass line of dark matter's gravitational pull. Evidence for these ideas is still speculative, but subtle clues are emerging. The cosmic microwave background's faint anomalies, those puzzling asymmetries in the universe's oldest light, might betray traces of this dark genesis. Some simulations show that a staggered origin for dark matter could leave distinct wrinkles in the large-scale structure of galaxies, patterns we're only now beginning to hunt for. Even more radical is the notion that dark energy's repulsive force might be a relic of inflation's final moments, a leftover energy that lay dormant for billions of years before reawakening to accelerate the cosmos. Skeptics argue these theories add unnecessary complexity, invoking unseen events when simpler explanations might suffice. Yet the allure of a dual-origin universe is hard to ignore. It offers elegant solutions to lingering puzzles, like why dark matter seems so indifferent to ordinary matter's forces, or why dark energy's influence kicked in so late in cosmic history. If true, it would mean our universe is far stranger than we imagined, not just expanding, but born from a hidden dance between light and shadow, each with its own origin story. As telescopes probe deeper into the early universe and particle detectors grow more sensitive, we might finally glimpse echoes of that dark dawn. Whether inflation was sparked by dark energy's ancestor or dark matter arrived in its own Big Bang, the answers could rewrite not just cosmology's first chapter, but the entire book of our cosmic history. Until then, the question lingers: did the universe begin with one bang or a symphony of them? The darkness may hold the secret. At the heart of black hole physics lies a paradox so profound it shakes the foundations of quantum mechanics, the information paradox. The problem begins with Hawking radiation, the slow leakage of energy that causes black holes to evaporate over eons. As particles escape, they appear to carry no information about the matter the black hole consumed, violating a core principle of quantum theory. Information can never be truly lost. In a universe dominated by dark energy, where black holes are the last structures to fade into oblivion, this paradox takes on new urgency. If information vanishes when the final black hole evaporates, does the universe fundamentally forget its own past? Consider a book tossed into a black hole. According to general relativity, the book is irretrievably crushed at the singularity, its information erased. Yet quantum mechanics insists the book's information, every word, every ink molecule must persist, even if scrambled beyond recognition. Hawking initially argued that radiation emitted by black holes is random, like thermal noise, leaving no trace of the book's content. This sparked a decades-long debate, with luminaries like Leonard Susskind proposing the holographic principle. All information swallowed by a black hole is encoded on its event horizon, like a cosmic watermark, and slowly released as the hole evaporates. But dark energy adds a sinister twist. In the far future, as accelerating expansion isolates black holes in eternally widening voids, their Hawking radiation will redshift into undetectability long before evaporation completes. The last remnants of information, if they escape at all, will be stretched across light years of emptiness, diluted beyond recovery. It's as if the universe sets a deadline: decode the information now or lose it forever to the expanding dark. Some theorists suggest radical solutions. Quantum entanglement might preserve information in subtle correlations between emitted particles, like a cosmic cipher waiting to be cracked. Others propose that black holes leave behind microscopic remnants, dense knots of quantum data that outlast the evaporation process. The most mind-bending idea comes from string theory, where black holes are tangled strands of energy whose information never truly enters the whole. It's holographically smeared across higher dimensions, safe from annihilation. Yet all these theories collide with dark energy's relentless expansion. If space stretches too fast, even the cleverest quantum recovery mechanisms may fail. Information could become so dispersed that no future civilization, no matter how advanced, could ever piece it back together. The universe's final act might not just be the fading of light, but the irreversible loss of meaning itself. This isn't just abstract physics, it's a battle for the soul of reality. If information can't be recovered, our understanding of causality and quantum determinism collapses. Every star, every life, every moment would leave no permanent mark on the cosmos. But if solutions like holography or remnants hold, the universe might safeguard its history even in the face of dark energy's void. The answer, if we ever find it, will reveal whether existence is fundamentally knowable, or if some mysteries are swallowed by darkness forever. Dark matter and dark energy aren't just gaps in our understanding, they're the chasms that define the frontier of modern physics. These 30 mysteries, from the ghostly fingerprints of the bullet cluster to the eerie uniformity of the cosmic microwave background, aren't isolated puzzles. They're threads in a vast, interconnected tapestry, each one pulling us toward a deeper truth about the universe's hidden architecture. Together, they paint a picture of a cosmos far stranger than we ever imagined, where the ordinary matter we see is just a flickering shadow against the dark enormity of the unknown. Solving these riddles isn't just about filling textbooks, it's about unlocking what could be the ultimate theory of everything. Imagine a framework that doesn't just explain galaxies and black holes, but ties together quantum mechanics and gravity, the infinitesimally small and the cosmically vast. Dark matter's gravitational whispers and dark energy's relentless push could be the keys to that unified vision, bridging the gap between the forces that bind atoms and those that shape the universe's fate. Every anomaly, from the Hubble tension to the too big to fail problem, isn't just a flaw in our models, it's a clue waiting to be deciphered, a signpost pointing toward a deeper layer of reality. The hunt for answers is accelerating. Cutting-edge experiments and observatories are poised to peel back the veil like never before. The Laser Interferometer Space Antenna, or LISA, will listen for gravitational waves from colliding supermassive black holes, potentially revealing how dark matter influences their dance. The James Webb Space Telescope's infrared gaze is already probing the earliest galaxies, searching for traces of dark matter's role in their formation. And the Vera Rubin Observatory's legacy survey of space and time will map billions of galaxies, hunting for the subtle distortions that betray dark energy's grip on cosmic expansion. These missions aren't just tools, they're time machines, offering glimpses into the universe's darkest corners and earliest moments, but the most thrilling part. The answers might not come from where we expect. The next breakthrough could emerge from a lab buried deep underground, where detectors strain to catch the faintest pulse of a WIMP. It might hide in the data from a quantum sensor, finally spotting the wave-like ripple of an action. Or it could lurk in the equations of a theorist daring to rethink gravity itself. That's the beauty of this grand cosmic mystery. It's not just about what we know, but how much we have left to discover. So stay curious. The universe's greatest secrets are still out there, woven into the darkness between the stars. Every observation, every experiment, every bold idea brings us closer to unraveling them. And when we do, we won't just solve a few scientific puzzles, we'll rewrite the story of everything.